Okay, well, let's start by finding an estimate for the magnitude of kT. Writing Boltzmann's constant in SI units and multiplying by room temperature 300 Kelvin. We could also take biological temperature, about 310. We get about 4.1 times 10 to the minus 21 joules. A joule is a force times a distance, or a Newton meter, and we can convert that to piconewtons and nanometers. And in those units, you see that the exponent cancels, and we're left with a much simpler expression that kT is just 4.1 piconewtons nanometers. And that's a very useful set of units to write kT in. Now let's use this in a calculation. So we found that the energy of a molecule of a gas is 3/2 kT. And we can ask approximately how high can you go up in altitude before you run out of oxygen? Well, that would be when mgh is about 3/2 kT, and that sets the height. So we can solve that for h as 3/2 kT over the mass of, say, an oxygen molecule times g in the denominator. And the mass of an oxygen molecule is 2 oxygens, or 0.032 kilograms per mole. A mole, using Avogadro's number, 6 times 10 to the 23rd, gives us 5.3 times 10 to the minus 26 kilograms for the mass. Substituting that in to the height formula, along with the other constants that we just found, gives us about 11,500 meters, which we can compare to the height, the same Mount Everest, at 8,850 meters. And you can see at that height, you've about run out of oxygen. For this third topic, remember we wrote Einstein's equation as zeta d equals kBt. And in this equation, basically all the quantities except for Boltzmann's constant, kb, are measurable, experimentally measurable. And we can use this equation then to solve for kb. And so this gives a number for Boltzmann's constant. Having that number, we can use that in another relation, the ideal gas relation. PV is RT for 1 mole, or PV is the number of atoms in 1 mole times kBt. And this relationship, or both of these two relationships together, will give us a estimate for the number of molecules in 1 mole. This is conceptually extremely important because this number actually makes no sense unless there exist atoms. Okay, for this next topic, we can note that since the kinetic energy of a molecule is 3/2 kT, it depends only on the temperature, nothing else, then we can say that the kinetic energy of a particle is independent of the phase that the matter is in. In other words, in thermal equilibrium. That is, if we have a container with water in it and gas in it, vapor, it doesn't matter whether we're looking at an oxygen or water molecule in the gas phase or the liquid phase, those molecules, whether they're in water or in the cell, in a biological cell, their kinetic energy will still be 3/2 kBt. Okay, for our fifth topic, let's do a problem. Let's do an example. And the question is, roughly how fast is a protein moving around between collisions in the cell? That is, what's its velocity due to the thermal energy? And we're given some constants there. Well, since we know the kinetic energy is 3/2 kT, we can solve that for the velocity like we did in lecture. And so there's the expression for the velocity. And let's put in some numbers. So we need to put in, first of all, kT, which we found already. There's kT. And we also need to put in a number for the mass. And now for the mass, we can use our numbers sheet. And we see that from our numbers sheet that there's about 100 proton masses per amino acid. And a typical protein has about 300 amino acids, or there's 30,000 Daltons in average mass of a protein, as you can see in the sheet. Or about 5 times 10 to the minus 23rd kilograms for the mass. So let's substitute those quantities into the velocity expression, giving us a velocity of about 15 meters per second between collisions in the cell. So you have to imagine this protein executing a walk of very tiny steps in between collisions where it's moving actually quite fast on the scale of the cell. Again, the speed between collisions for very short distances, the mean free path length; for very short times, the mean free path time, tau. Okay, for this last topic, we're going to kind of sketch out the solution to the Navier-Stokes equation in a certain limit. The Navier-Stokes equation, which we won't really have time to derive in our class, but I'll write it anyway, is given by the density rho of water times the Lagrangian derivative, at least what's called the Lagrangian derivative. It's rho dv dt plus rho v dot grad v, and that's equal to minus the gradient of the pressure P plus the viscosity eta times the Laplacian of the velocity v. Again, it's a bit, that's a complicated equation, and in fact, it's quite intractable in general. But as we'll derive, there's a limit when the left-hand side is much smaller than the right-hand side, or the inertial terms in the fluid are much less important than the viscous terms. That limit is characterized by the Reynolds number, which is equal to rho v a over eta, a being the scale of the length scale of the system, v the velocity, rho the density, eta the viscosity, and it's almost always much less than 1 in the cell. And in that case, the left-hand side is much, much smaller than the right-hand side, and solving the Navier-Stokes equation just amounts to solving the right-hand side is equal to 0, or grad P is eta del squared V. So let's imagine flow past a sphere of radius A, of say water with density rho. And here I'm drawing it out. And we'd like to solve this equation for this particular example. I won't do it, it's kind of beyond the scope of the course, but I'll sketch it and show you what's involved and the result, which is important for our course. The fluid's also incompressible, so its divergence would be equal to 0. It has to be 0 divergence, and we'd like to solve those equations subject to boundary conditions, or BC's, boundary conditions, where the velocity can't penetrate into the sphere. The sphere is incompressible, so VR, the radial component at radius A, is equal to 0, impenetrable sphere, and it can't slip across the sphere. The water sticks to the sphere, so V theta at radius A is equal to 0. That's the no slip condition. There's another boundary condition at infinity, which is that the fluid flow has to be, say, in the z direction. I think I've turned the z around there. It should be facing the other way, but anyway, in this spherical coordinate system, v is in the z direction. The radial component at infinity is v naught cos theta, and in spherical coordinates, the polar angle component is v naught sine theta. And those 4 equations there give the boundary conditions. And solving this, even this equation in this simple limit, is non-trivial. In fact, it turns out that something like a third actually, of the force comes from the fluid pressure component, and 2/3 of the force, drag force, on the sphere comes from the viscous dissipation. So again, a non-trivial solution for the sphere, or the flow past the sphere of velocity v, or equivalently the sphere moving at velocity v through the fluid. But the solution then is that the drag force is minus 6 pi eta a times v, a being the radius of the sphere, v the velocity of the sphere. Noting that F is minus zeta v, this gives the friction coefficient zeta as 6 pi eta a. And that was the result that we were after, namely the friction coefficient for a sphere of radius a in a fluid with viscosity eta.